Okay, the good news is example 2 is worked out fully in the book. The bad news is I want to work through it together. That way we can talk about it instead of read about it. Any luck? Okay, hopefully it's on his desk or something. Good luck. So, once again, we have a couple tasks. We got to make an estimation, then we got to talk about the error in it. Oh, and this time we'll have a third one. We want to further talk about reducing the error. So let's at least start with the first task. We need this polynomial and we need to use it to approximate something. So from page, what was it, 42? I never get it right. 40. You know, my head said 41. I was like, no, that's the one you guessed last time. It was wrong. 42. Nope. Okay. So from page 41, we already know a Maclaurin polynomial for e to the x. We know e to the x is about, and that's the one where it's power over factorial. So like it'd be x0 over 0 factorial, x1 over 1 factorial. And it says to use the third degree, so I'm going to stop there where n equals 3. And I wrote it out this way just because that's how I would memorize it. I would just memorize the general term and then list it out. And then I would say, okay, that's really 1 plus x squared over 2 plus x cubed over 3 factorial. Well, if our job is to approximate the square root of e, what should we do to do that? So we should plug in the thing we want to approximate into it. 1. So that would be if our polynomial is for e to the x. Basically, I'm asking you, what are we going to plug into x? There we go. Square root of e, that's the same thing as e to the 1/2, no? Yeah. And if we want to estimate e to the 1/2, then let's plug in 1/2 for x into our polynomial. So, well, I need to turn this camera a little more. There we go. All right, so our third order polynomial evaluated at 1/2 would be 1 plus 1/2 plus 1/2 squared over 2 plus 1/2 cubed over 6, or 3 factorial. Which again, I'm going to make the same hand-wavy argument I said yesterday. We could take the time to do the multiplication and the division. Let's assume we just have a 4-function calculator. Pick up your calculator, push the buttons. You'll get either a fraction if you're in fraction mode or a decimal if you're in decimal mode. This is about where it should come out. And then the 3 starts repeating at the end. So our estimation of the square root of e would be a little more than 1/2. So it's what? So that's our first task. We have done it. There is our approximation for square root of e. For the record, if you want to check, we could real quick. Square root e. Okay. Not the worst thing in the world. Oh, it doesn't project well, but 1.64, 1.64. Okay, so we're good for the first 2 decimal points. It's the third one where we start to fall off. Oh well. Let's see. So then our next job is to talk about how much error there is. And okay, this is a mistake on my part. I should have said, what's the error bound? Because that's what I wanted us to talk about, is the error bound. Obviously, the true amount of error would be answer minus calculator's number. So how much error, how about error bound is in our solution? Oh, I zoomed in a little bit to get the calculator. Come on back. Come on back. There we go. So if our job is to estimate the error in our solution, then we'd go back and borrow our formula for error. This guy, our Lagrange error bound. So that's what I'm going to work on right here. So this would read the bound magnitude of the error in the third degree term, or sorry, the third degree estimation evaluated at x is 1/2 is less than or equal to, and this is our job. Our task is to figure out what is that error bound. We know from the formula would be m over n plus 1 factorial times the absolute value of x minus a to, again, the n plus 1 power. So let's take care of all the easy stuff first. We know n, we know x, we know a. N is 3. Okay, so we have m over 4 factorial. I guess we don't even need the absolute value bars because, again, n plus 1 is going to be 4, so an even power would give you a positive number no matter what. You could certainly leave the absolute values if you wanted. And then our x was 1/2, and our a was 0. Remember, our job is to pick the value for m. We need an m that is an upper bound of the n plus 1th derivative. So here that'd be the 4th derivative. Well, I shouldn't have put the period there. Between x equals 0 and x equals 1/2, because that was our center. That's where we evaluate. Whew. So, what's the 4th derivative of e to the x? Okay, so we can just jump right there, right? f4 of x, still e to the x, and now let's think about this. We need something that's an upper bound, something that's either equal to the maximum or definitely bigger than the maximum value on that interval. E to the x is a strictly increasing function, right? So really, we kind of just need to look at the endpoints. The left endpoint would be e to the 0, which is 1. Okay, but that'd be our minimum value because it's strictly increasing. And our right side would be, oh, dang it. It'd be the thing we're trying to estimate, right? Okay, so in a perfect world, obviously if we could just use that value, we'd say m equals the square root of e. But it'd be kind of dumb to use the number you're approximating in your own approximation of the error, right? So, could you, sorry, what?
Are you allowed to pick one that's also going to have error in it, or do you have to pick one that works?
It would be best to pick one that works and is nice. So, the author makes the following argument. He says, we know E on our calculator is about like 2.718, right? Which really means it's smaller than 3. Okay, so if we're talking about the square root of E, we could use the square root of 3. But again, that's a problem. How do you generate the square root of 3 if you're assuming you can only use addition, subtraction, multiplication, division? How about we just use 3? 3's still got to be a ceiling for the square root of E. Because E itself is smaller, so of course the square root would have to be even smaller. So let's start with m equals 3, and then I'll give you a better one too. But we know 3 would definitely work. 3 100% has to be bigger than the square root of something smaller than that. Yeah. I'll come back to that. I'll come back to that because you're knocking on the door of the better way to do this. Okay, so then revisiting our error statement. So here's our error. We filled it out up here with the exception of m, so let's just plug in 3 for m. And let's see what that comes out as in the calculator. Okay, so 3 over 4 factorial times 1/2 to the 4th power. And I would prefer that to be a decimal. Okay. That's not bad. Again, our error is at most something in the 3rd decimal place. But it could be better, right? How about this? Well, if e itself is less than 3, surely it is also less than 4.
No way.
No, I mean, this is giant, right? I know. No, I thought our idea was to make the error better, not worse. Well, we're talking about the square root of e, no? So then would not the square root of e be less than the square root of 4, which is 2? So you could run it again with m equals 2. So I'll just recall the previous line in my work. I'll switch the 3 to a 2. Let's just see how much it changes. Little bit of an improvement. Still not amazing, but it's all right. Let's look back at our last task for this problem. What degree, because, okay, hang on, before we look at the task. The only way we could continue to make the error smaller is to either find an even better m, which is smaller, or if we just increase how many terms we use in our polynomial, that's going to make our factorial bigger, which means we're dividing by a bigger number, which means our error will definitely get smaller. So, in that vein of logic, our last question is, what degree should we use to get an error less than the 3rd decimal point? You know, the thing, the accuracy we're always looking for, right?
Wait, can you run your fraction for me?
Sure, it was 1 over 192 and
That's divisible by 28.
1 over 128. I appreciate that you might be like one of 3 people to prefer a fraction over a decimal in the last like 5 years, but I'm just giving you a hard time, man. Okay, so again, our last task is, what is wrong with this pen? Oh well. So what degree is going to give us an error bound less than 0.001? That's our last question. How do you think we should solve that? I mean, that's kind of how we're going to brute force it. We're also going to use these 2 guys' ideas. We're kind of going to wrap them all up into one. Let's take, she said, well, you got a formula for this. Let's we could set it equal to 0.001 and do some solving, or we could guess and check a bunch of, we could just increase n by 1 every time and see when we get there. But we have a formula for this already, right? Let's keep using m equals 2 since we know it's good. And we know, okay, so what's going to be different this time is we're not specifying n. But we are still specifying m and everything else, x, a, all that good stuff. So we know the error, no matter what, is going to be less than 2 over, again, you don't know the n this time because that's our job to pick it, so let's leave the factorial in there, times absolute value. Let's see, x was 1/2, a was 0, so I'm just going to leave it as a half. Well, I guess I didn't need the absolute value, but whatever. This is a one variable equation or inequality. Now again, we could pick the values, and to evaluate them it would just be multiplication and division. So we're going to use this guy to help us out with those 4 functions. Let's just, if that's a one variable thing, can we graph that? I mean, it's weird, it's got a factorial in it, but we'll get over it, right?
Will we be allowed to graph this on like the test?
Yeah. If this was your task, absolutely.
Oh my god. Oh my god.
Okay. So let's take a look at what that looks like. Don't you love have to do this the old school way since I'm using the iPad? So I punched it in. There it is, 2 over, now I had to use x instead of n, of course, just since I wanted to graph it, but whatever. There's my 1/2, there's my exponent, x plus 1. I press enter. Oh. Well, that's underwhelming, right? Well, you also have that table function on your calculator. Control T. Yeah, there we go. There's our values. So like, if we use the first power, we're off by 1/4. I know it's kind of hard to see on the projector, but hey, there's our answer for 3, right? That's what we actually did earlier. That's how much error we got. And looks like the 4th degree would be the first one that gives us the desired amount of error. It would give us error less than 0.001. Oh, whoops, I'm way zoomed in. Fingernails. Okay. Just to kind of debrief overall here. With these style of tasks, it's usually fairly obvious what you should use for M, or College Board gives you something you should use for it. Yes. But, of course, it's still on you to remember the rest of the formula. So like here, it wasn't obvious that we should use 3 or 2. I'll give you that. But what did help us was we had a function which was strictly increasing. So really all we had to know was the left and the right heights of the function. So then you know a minimum and you know a maximum. And then you can like check both of those and go from there. All right, what else do I want to do? God, I gave you so much. I don't know if we need to do all these problems, but let's see. I want to. Okay. Yeah. I got to figure out what we're gonna do next. So, hold up. All right. Yeah. I will go ahead and do this. Okay. We turn the page. Here's another problem for you. I would like for you guys to try this either by yourself or with the person you're sitting next to. Approximate a value using a Taylor polynomial centered at x equals 1. Notice it's not a Maclaurin, it's a Taylor polynomial centered at x equals 1. You should not have to build it from scratch. You can just adjust one of the Maclaurins to get there.